This chapter is really a very interesting one in that we're looking at internal threats. And what had been talked about earlier on the last time is here are all of the reasons that you might think you have results and you don't really have them. And sometimes it can be the case, though, that you don't have results, and this is because your design has kind of sabotaged you in some form or fashion. So if we get into some of the more specifics of that, here's three reasons for you not finding results when in fact results might be there. Measurement error is one of the things that can really kind of mess up your study. And this is the reason why, if we're doing an experiment, you want to make sure that the measure that you are using is reliable enough to do an assessment that can be believed in. There's a bit of a trade-off here, and we'll talk about that a little bit more, but to gloss on that a bit, if you're doing a really large study, it's often okay just to have a single item to measure what you're looking at. If you're doing a smaller study, it's probably the case that you'll have to ask several items or really control your measurement in order to be able to have enough power to find the differences that might be there. So we'll talk about that within the context of trying to control the conditions and what I would like to call the bandwidth fidelity problem. That is, you can measure something really, really precisely, but at the end of the day, you've taken up an awful lot of your experiment just doing that assessment. And it's in the real world, it's often a trade-off. Shall I ask fewer questions, have slightly less reliable measures, but yet be able then to extend my study to include more variables in it? Because the more variables you include, the more you can address some potential confounds. Another thing that can be a problem are individual differences. So if I'm looking at a school that has a wide variety of levels of ability of children, or a wide variety in, say, the anxiety that children might be having, that variation is going to make it harder for me to detect differences between, say, an experiment and a controlled school, for example. Situation noise also happens. So, what's an example of situation noise? In this day and age, whenever we go into some places like the hospital, or I donate platelets at the Red Cross, they come in and the first thing that you have to do is to get your temperature taken with one of those little forehead scan things, and they'll kind of halfway swipe it and go and look at it and go, oh, that's not right, let's do that again. Well, if you're just coming in from outside, you're a little bit colder than you would normally be. Maybe you need to wait before you can settle in. Maybe it's the case that you need to do more repeated assessments to get at that situation variability. For this reason, that's why we bring people into the lab, and why the lab is a very standardized place, because you wouldn't want to say, oh, I'm going to collect one piece of data, say, out on the quad, and another piece of data in a lecture hall, and another piece of data in the local Starbucks, because each of those situations is going to affect how people respond a little bit. And to the extent that the situation that you're in determines the answer that you give, that situation noise gives you more variability in performance. So the name of the game here is you want to design your study so that you have a minimum of variation inside your experimental condition and inside of your control condition. And you also want to find that you've got a lot of variation in comparing the experimental and the control conditions. And these have to do with increasing power. If you think back to your earlier statistics class, alpha, type 1 error, is the odds of declaring that there are significant differences when in fact none actually exist. So we set our alpha at 0.05. Psychology, statistics is the only discipline where we insist on the right to be wrong about 20% of the time. P equals 0.05. Power, on the other hand, is the odds of being able to correctly identify differences when they exist. 1 minus power is called beta, and that's the odds of a type 2 error. That is, declaring that there are no differences when in fact differences do exist. That's just a little bit of a review of your earlier education. So as I mentioned before, if you're trying to do an assessment, it's important that that assessment be an accurate one. This is the reason why, for example, finals are 2 hours long rather than 1 hour long, that hopefully over the course of a longer assessment, we can get more precise, reliable measurements. Sometimes, in addition to just instruments, if you're using observations, you want to be able to watch observations over a longer period. And this is particularly true if you are measuring elderly people or if you're measuring children, because children and elderly have a lot of performance variation going on. And if you can get a longer period of time of assessment, you'll have a more accurate picture of how people are responding. So I've got a couple of pictures to show you here. Individual difference, so this is the slide from the book, figure 1116, that if we're looking at mood from not being given any money and being given money the day before, a lot of variability exists at the individual level. Now, to the extent that individuals differ just in terms of how happy they are, it's going to be hard for you to find statistically significant differences between these two groups. I don't know how you are, but visually for me, I kind of like to think about taking these plots and making a little probability density plot or a little diagram of what that would look like if I would put it on the y-axis. And if we do that for the blue dots and for the red dots, we'll see there's an awful lot of overlap going on here. And to the extent that you have a lot of overlap, that's going to be a problem. Well, one way to do this, to adjust for this, is to change your study from a between groups design, where I'm looking at Michael in one group and Candace in another, and coming back and looking at a longitudinal study of repeated measures, where on one day I don't give people money and on another day I do give them money. Subject, of course, to balancing the order in which you have these things. It becomes a little bit easier to see that after I adjust for general level in happiness, receiving money on average makes people a little bit happier because those scores are, by and large, going up as a result of that. Now, let me come back and go to this little picture. Another way to control for individual differences is to use what is called analysis of covariance. So let me walk you through this little picture because I think it's somewhat helpful. What we have are 3 groups here, a red, a green, and a blue group. And what we're interested in knowing is whether there are differences between the red, the green, and the blue group. Well, generally speaking, if we kind of use our trick of taking all of these dots and pushing them onto the y-axis, there's an awful lot of overlap between the red, the green, and the blue group. But visually, as I'm looking at this, I would say, well, no, hold up a minute. All of these blue dots are a lot lower than all of these green dots, and the green dots are kind of sort of a little bit lower than the red dots. So how might I use some statistics to answer that question. And analysis of covariance does the following. It takes everybody's pretest score and calculates a residual score on the post-test score. So I'm going to do a little regression. I'm going to predict post-test from pre-test, and I'm going to record these numbers, positive and negative numbers, essentially smooshing all of this into a mean down here. So another way I can think about that is kind of taking my fingers and pushing all those lines together and calculating a mean down here for all of the blue people. And I'll do the same thing for the green folks and for the red folks. And when I do that, after I've kind of squeezed all of those blue dots together away from the line, that's going to give me a distribution of scores that's going to have almost no overlap with the greens and the reds. And similarly, after I squeeze the regression line down for the green group, that distribution is going to have a lot less overlap with the red distribution than it did if I was just looking at all of my post-test scores here, here, and here. So in terms of going back to the diagram here, if I'm worried about variation, if I just say, hey, I'm interested in the question of whether getting money will make you a little bit happier, but some people just sort of walk through life a little bit happier than other people walk through life, and I need to control for that. My strategies are, I could do a within groups design, that is, I can expose each person to both conditions, or I can use analysis of covariance, that is my little picture here, and take these dots and squeeze them along that line in order to get a distribution of scores that doesn't have as much overlap. Or I can come back and I can use a matched groups design. So maybe during the mass testing in site 1, I would give my happiness mood score to people, and when I do my between group study, I'm going to assure that a very happy person in the no money condition is matched to a very happy person in the $1 condition. But again, our goal here is to be able to take these data that we collect and reduce variability inside condition so that we can detect variation between conditions. Okay, the first chart you showed us, the one with the vertical lines, I'm a little confused about how to interpret that. Okay, this one?
Yep.
That's it? Okay. So in this study, the way it's done in 1116, I did what's called a between groups design. I had 6 people in the no money condition and 6 people in the $1 condition. And if I want to compare the no money with the $1 condition, I would be looking at the average of all of these blue dots and the average of all of these red dots. And the mean here is not going to be that different from the mean here. And the important thing to keep in mind is there's an awful lot of variation inside of each of these conditions. And the more variation there is inside of these conditions, the harder it will be for me to find a statistically significant difference between these two conditions. Is that working?
Yep, that's great.
All right. And then downstairs, so the reason my study didn't work here is some people are just happier than other people in life. And yes, it's kind of nice to know that, but what I'm interested in is if I give them money, will they be happier? And in order to make that test, I'm going to try to reduce the variation inside of the no money condition and inside the $1 condition so that I can find that effect that I'm looking for with a little more power. So here's one way to look at it. If I use the same person, that is, I use what's called a within groups design, now I can calculate the slope of the line as kind of a measure of, is this going to be statistically significant or not? And we see that for Michael and also for Candace and for some of these other people, it looks like everybody's just a little bit happier across those conditions. So one way to, I mean, if this were the before times and we were at a blackboard, this would be a little bit easier to do, but I don't know if you're seeing my cursor, but if I take all of these people in the no money condition and I squeeze those points together, and in the $1 condition, I squeeze all of those points together, on average, there's going to be now very little variation in the no money condition and in the $1 condition, and I'll be able to see that modest gain in happiness, thus resulting from the condition. And I've adjusted for the fact that some people are just happier than others. And if I come back to this picture, I'm kind of doing the same thing, but with a pre-test on the x-axis and the post-test on the y-axis. So these people here, if I adjust for the pre-test variation, I'm going to be essentially taking these numbers and squeezing it along that blue line. And I'll have a distribution of scores here that will be in the average of the pre-test for those folks. And there'll be very little variation now after I've squeezed that blue line, all of my data points along that blue line. And if I do it for the same thing for the green and the red, after I've done that, and then I kind of project or move them onto the y-axis, I'm going to have very little overlap between the blue, the green, and the red groups. If I don't use analysis of covariance and I squeeze all these numbers, there's going to be an awful lot of variation inside each of those groups. And just as for that other example, that individual difference, that pre-test score, is going to make it harder for me to find statistical significance if I just analyze only post-test data. And sometimes in experiments, I can't change this to a within groups design. So as I mentioned before, sometimes in experiments, we lie to people. We tell them, do this little maze test, and it's a measure of your intelligence, and we're interested in people's attributions about how they get told the results of the test. Do they get discouraged? Do they get very happy, even though the test has nothing to do with it? Well, if your two conditions are, you just say, take this experiment, and then you tell them, regardless of how they did, oh, you did very poorly, or take this study, and oh, you did very well. You can't turn around and say, and now for a new condition, do the same test again. I'm going to tell you did really well, because people will know something's up. Well, if I can't reasonably put the same person in conditions, the next best thing is to try to find some matching strategy. So rather than looking at the same person in the no money and the money condition, I might find someone with a happy mood score on a pretest, and I might assign one really, really happy person to the no money condition, and another really, really happy person to the money condition, and the same song for the least happy person. There's going to be this, I'm randomly assigning, but on a matching strategy. And this accomplishes the same thing. I just don't have the same person, but I have somebody who's pretty similar to that person. Anything more? So sometimes you can't match, sometimes we need to think about other strategies for making that comparison. Well, one way to reduce the size of a confidence interval is to reduce the variation. Now, these are the strategies that we just talked about. I can do some more precise measurement. I can try to put people in the same lab situation. And I can try to do the matched groups design or do it within groups design. Another strategy for reducing the size of your confidence interval is to simply go out and test some more people. The more people you have in your study, the more likely it will be that you can find statistically significant differences when they exist. And if you also want to change your ability to find statistical significance, you can adjust your p-value. So it helps to kind of see some things out here, and there's an awful lot of apps that are available on the web. Here's one that I wanted to show you. I think I'm on that one. Where did it go to? There we go. So here's an app for comparing some independent samples, and you may have experienced this in your earlier class. So what I might be interested in doing is to answer the question, how many people am I going to need in order to detect a difference between two groups? And the way we do that is to make up a number, say 10, for what we think the mean of one group is going to be, and make up another number, say 12, for what the mean of another group is going to be. And what I'm going to do in here is put in a standard deviation, say 1. And I can then calculate, and then down here, here's my alpha. And down here is the power that I want to have. In other words, I want to ask the computer, how many people am I going to need in order to have a power of 0.8? That is, to be able to say there are differences in this group when in fact they do exist, when in fact the mean of one group is 10 and the mean of the other group is 12. And I can hit the little calculate button, and if I have a standard deviation of 1, I'm only going to need 4 people in my experimental and control group. If the standard deviation is larger, at 5, I'm going to need 99 people in each of the groups. So if you're wanting to play with this yourself, here's the link for that particular website. Now, the more differences there are across these two groups, if one group is 10 and the other group is 15, for example, I'm only going to need 16 people in each group. Now, the other thing that she talks about is, well, another way to get away with having fewer people is to play around with the alpha level. So if I said, instead of a 0.05 significance level, it's only 0.1, I only need 13 people. And conversely, if I decrease the alpha level and say I want to know what's significant at the 0.01 level, that's going to mean that I'll need to have 24 people. And I thought, it's kind of nice to sit down and play with this little app. It's not the sexiest graphical thing that's out there, but it does bring home for us the question of, if I have two means, the smaller my standard deviation, the fewer people I need, that is, the less variability within condition, and the larger the difference between the two groups, the fewer people I would need. Does that help? I'm looking for an amen. Okay, thank you, Grace. Right. So, situation noise, any kind of distraction that can cause variability within groups, if it's used between groups differences, and we can control for that by controlling the experiment. The other thing that we can do, the other thing about situation noise is that maybe the measurement occasion, the day of the week that you're looking at, is a significant source of situation noise. So if you're doing your study and you're looking at a behavior that seems to vary a lot by day of the week or vary by hour of the day, then if you're designing your study, you probably want to have your experimental and your controlled people exposed to those times about the same. Well, what are some examples of that? Well, it's a little bit easier. In my life, we look at drinking. Well, truth be told, if you're asking somebody, did they have a drink last night, and you're asking this on Friday, you're going to get a lot more responses than if you're asking that same question on Monday. Mainly because we have a Thirsty Thursday thing. Some of our curators shamefully have invested interests in some of the bars in Columbia and Kirksville, for that matter. And they're catering to the academic schedule. In addition, for some odd reason, if you're looking at the zoo, the amount of drinking that goes on in the winter is higher than the amount of drinking that goes on in the fall. Is that because things are really cold outside, there's nothing else to do, you can't go out and do anything? Or is that because perhaps some of the drinking is more strongly associated with some sports events than other sports events? We also control for spring break because an awful lot of the unexamined life gets explored during spring break on average. So if you're doing an experiment again, you want to be keenly aware of what's going on with these history effects. And if you're doing an experiment, to make sure that you either avoid particular times that are going to be really, really different, or you control for it by making sure you've got people in the experimental and the treatment group who are both being assessed during that time. So, wait a minute. So if we were to spend a little bit of time going through the obscuring factors and how they can result in null effects, well, I can kind of walk through and give examples of this. It's in table 11.3, but if I didn't really manipulate my independent variable that well, then it could be the case that I'm not going to find the effects that I'm looking for. So in the case of reading games, if you're only having people do it for a couple of weeks, maybe you haven't really assessed it long enough to find the effects that are there. And as you're looking at it, things to think about are, how do I know they really manipulated the independent variable? And did they have any manipulation checks in there to make sure that what was done is really done what was intended? Second, maybe they didn't use a sensitive measurement of the dependent variable. Well, in psychology, since I do a lot of work in psychopathology, one of the problems there is very often psychiatry, abnormal psychology, is in love with the 0-1 variable. Are you depressed or are you not? Do you diagnose with this psychological disease. That's the way they used to talk about it. Well, there's really, really wide worlds of difference in terms of depression. So, my mother, for example, kind of being from World War II and so forth, suffered from depression quite a bit. There were days when she couldn't get out of bed physically. Well, that's an awful lot different than, say, people who are, not having a fun time and report that they're depressed and that something's really, really bothering them, but they're physically able to get out and move around. Well, there's probably some gradations of depression that is obscured by that issue of diagnosis. If you want an excuse to be kind to people, that 0-1 variable is something to think about. So roughly half of our freshmen diagnose as being psychologically distressed. And that's very significant. I mean, coming to campus is a hard thing for people. Now, happily, most people recover from that experience as they adjust to the new situation that they find themselves in. But, the point is that in terms of designing a study, maybe I don't find differences between depressed and non-depressed people using my particular medication or my particular therapy, but that might be just due to the fact that I'm measuring depression with a 0-1 variable. Maybe what I need to do is use an instrument that has continuous values, and that increased precision would allow me to find things. Maybe ceiling and floor effects exist, and the instrument that you are using is ill-suited to the construct or the population you are looking at. So, this happens in spades in higher education all the time. It is difficult for me when I teach graduate statistics to figure out where people are at. That's why, I ask you folks, I know lots of stuff, but what I don't know is what you don't know or what you're unsure of. It's very easy to ask a test that has floor effects going on. Psychologically, it's a little difficult to understand this given maybe all of our experiences in higher education. But if you ever take a testing class, the best items on a classroom test are those that only half of the people in the class answer correctly. Those items will have the most discrimination between students. I used to take, when the Aristotle crust was cooling and I was an undergrad, classes from a new professor, and he would ask tests that, the average score was something like 16, and it was, a 4-item multiple choice test. Well, those things had, an incredible floor effect. You didn't really assess anything that you learned that was any different than anybody else in the class because everybody was getting a really, really low score. Conversely, we've all had those pleasant classes where, the professor's kind of a kind person and you're not going to be challenged. As a matter of fact, you get kind of bored and everybody gets an A. Well, again, you're not going to be able to tell who learned more than anybody else based on that particular type of instrument. Good instruction, I think, is a balance of things. It's enough challenges that you engage with the material, but enough supports that you're motivated to keep going on. All challenges is just kind of like drowning, and all supports is really, really boring, even though you think at the beginning, oh, hey, this is nice, it's an easy A. And these things can happen. This is the importance of looking at piloting your data if you're doing a psychological experiment. You want to use some manipulation checks. You want to have your participants give you some feedback as to what this instrument is like and why they answered the way they did. And ceiling and floor effects can exist both on your independent variable, maybe your conditions. So the example that she gives that's easy to remember is, we tell you we're going to give you a 10 volt, a 50 volt, or a 100 volt shock. Well, these makes everybody very anxious regardless, mainly because they don't know what a 10 volt shock feels like. And as a result, you're not going to find any differences as a function of the voltage condition. In the same fashion, ceiling and floor effects can also happen on the dependent variable, on the test that you're taking, which are the examples that I've been talking about here. So, measurement error, did they use an instrument that had an appropriate degree of measurement error going on? So what you're looking at here is if it was a very large sample, like those YouGov surveys or Gallup polls or Roper polls, they might only ask one question about what's your attitude toward the proposed stimulus plan. And that's enough because you're asking thousands and thousands of people. But if you're having a smaller sample, say I'm looking at 20 people in each condition, you probably want to make sure that you ask about that topic in a variety of ways so that you reduce the amount of variation just due to luck of the draw, asking someone about one particular question. We spent some time before talking about individual differences earlier in the lecture. And if you're, looking at these individual differences and you have null results, did they take into account all of the reasons why people might be different? And the nicest thing that you can do if you have the luxury of the time of assessment and you have an intervention that is not going to react with people is to have people repeat the study across the conditions, because a within groups design is going to control for all those individual differences in, say, motivation and ability and all the other things that make any one of us different from anybody else. And situation noise, well, could you, if as you're looking at the null results, did they put as many controls as they could in to control for some situations that might make the responses inside each condition be more variable? Or, the thing that stands out for me, given the research I do here, is looking at the particular time that you're asking about the behavior. There are some people who go out and drink on their 21st birthday, for example. So do you want to make sure that you ask people their birth date when you're assessing their behaviors? Because maybe if, the past week has been their birthday, that behavior that occurs on the 21st birthday might give you a lot of variability inside conditions. Now, down here at the bottom, if you're looking at your variable, maybe it's the case that your independent variable has no effect. And, did these researchers use a really large sample and take precautions to maximize between groups variability? So if you're looking at this and you're evaluating what's going on, you need to think about what that independent variable is in light of other studies. If you're looking at an independent variable that's operationalized a lot different than how everyone else is doing it, maybe that's the reason why this particular study had a null effect. And if the independent variable does have a true effect on the dependent variable, but you've got a lot of errors of sampling or variation, maybe this study didn't detect it. Well, hopefully, this is a problem. This bottom line is a statement about the statistical validity. A certain proportion of the time, given your study, you are going to find a really low or a really high value. It's going to be outside the confidence interval that other studies might have, but this is entirely just chance variation. So when you have a lot of studies, you can start to make some conclusions about what that looks like. So to sum up, and we're getting kind of close to the end here, power is the likelihood that your study is going to find a statistically significant result when the independent variable really has an effect. So power in this situation is the odds that I'm going to be able to say there are differences when in fact those differences are there. If I've got really large samples, then I'm going to be well powered. If I try to design my study so that the variation inside condition is small, that's going to give me bigger power. And if you're going to report null results, I'll admit I'm a little bit less optimistic than Dr. Morling about publishing null results. I am, by the way, trying to get one published. I just submitted it yesterday. And that particular null result is going to be, the conclusion was, in the state of Missouri at least, it does not matter what the characteristics of the community you came from are, and it does not matter whether you are urban or rural. What matters more is what your grades are in high school and what your academic aptitude is. There's a little bit of an issue for first generation. Interestingly enough, if you're looking at alcohol, being a first generation student is kind of protective for women. They are less likely to be as alcohol involved. But if you're going to report those null results, you had better make darn sure that you didn't just do a crappy study. So you've got to convince a reviewer that, yes, the instrument that I'm using is appropriate to this population. The dependent variable has some variation on it. It doesn't have ceiling and floor effects. Conversely, also, I don't have an influential observation, and I don't have outliers that contribute to an overestimate of what the variation is. And I have control for as many other variables that could be at work as I could. So it's work, but these are the things that you need to do if you're going to come to a journal and say, hey, we ought to be looking at this. And I don't remember whether this is on this slide or the next one. I'll just flip and take a look. Nope, it's this next one. So null results are kind of surprising in that sometimes where we find that people are actually comparable, it speaks to the external validity of our study. So I can be a little bit more comfortable in my conclusions about college drinking that I'm looking at by saying, well, it kind of looks like leading the unexamined life is a risk regardless of where you come from and regardless of what the characteristics of your school are. Journals are increasingly likely to publish this kind of stuff, but it's very difficult because you must make the lawyerly case that you did a darn good study, you controlled for as much as you could, and the results of this are very small. I mean, the reason that journals need to publish null findings when they happen is called the file drawer effect. Come back here. And what that means is, if I have a whole bunch of studies and I only select those studies that find statistically significant differences, I'm going to overestimate what the effect is if I systematically throw away null findings. So when somebody does a study and there's null findings in there, it's important that we get that information out so that we have a broader picture of what these relationships are like. Null effects are not sexy. So you're probably not going to find a USA Today breaking article about the latest null findings. And for that reason, they don't get as much press. But this is also some of the value to you of going out and finding your own research when you're doing your own kinds of searches. Right? So that takes us through